Mike has always been in Cambridge, UK, except 1 year in Cambridge, Massachusetts, at MIT, just not to change the town, the city. And well, he's gonna speak about the rise of electronic structure calculations.
Well, with the mention of MIT, then I was introduced to the field of electronic structure by Professor John Giannopoulos, who died just a couple of weeks ago. And so I want this talk really to be a tribute to him. Okay, so I want this talk really to be a tribute to him. He played an amazing role in the sort of 70s and 80s in our field. And the reason that perhaps the younger people here don't know the name so much is that he then moved on to the field of photonics. But he was an absolute role model of how to look after younger researchers and nurture them and mentor them. So as I say, this really is a tribute to him. So we have had a wonderful talk from Ali about theoretical chemistry. What I really wanted to do was sort of just give an overview of the rise of what we call electronic structure. I mean, that's just code for quantum mechanical simulations of condensed matter extended systems. So of course we have to be slightly different in the way that we approach it compared to the chemists. And of course, yeah, this is something that has been contributed to by hundreds of people over the years. And so a bit like Jens Norskov, I can only pick out a number of names and a number of things. And there is obviously a bias towards the people in Cambridge. So Volker, who joined us for dinner last night, I don't think he's here. And then Richard and some contributions from me. So the rise of electronic structure. And of course, it all really starts with this rogues gallery of the early people who together put together the ideas of what we now call quantum mechanics. Apparently this year we're celebrating 100 years of quantum mechanics. I have slight issues about that, but you know, I'll leave that for a national fight between France and Germany. Okay, but of course there is the Cambridge connection from the very early days of quantum mechanics. As Annie mentioned, Paul Dirac and his Dirac equation, and hence a model of spin, previously completely ununderstood, known to be there experimentally, but no explanation of it at all. And I mean, this quote from Paul Dirac, you know, is put up everywhere. You know, basically, we solved everything. You know, it's this equation. Actually, we can't solve it, but you know, it's all right. You know, everything is done. Well, except for high energy physics, right? So low energy physics, entirety of chemistry, which you all know is a subset of physics anyway. So that's fine. And it's kind of like, you know, this is Paul Dirac being Paul Dirac, you know, typical mathematician, right? But it's actually unbelievably unfair because he immediately afterwards said that what we need to do is find some practical methods of applying quantum mechanics that give you an explanation of the features of complex atomic systems. And of course, Ali gave lots of examples of work in chemistry that did precisely that. And I think, you know, this is sort of something that Kieran Burke said. It's you know, yes, it would be nice if we got everything to machine accuracy in 2 years' time with all the quantum computers working, then we will, you know, and that'll be fine, and then we can all retire. That was slightly facetious comment. I don't think they're going to be that soon. But really, the question you should be asking is my calculation sufficient to get some insight and make progress in the field? And that will be entirely problem dependent. And I think it may be something that comes up tomorrow afternoon in the industrial session. You know, as academics, you want to beat every problem with submission, but you know, that's not always necessary to actually make progress. So it can't be difficult, can it? All right. Well, except it is difficult because when you look at a solid, then you have two problems. Well, one problem is common to all of us. You know, technically, in terms of scattering cross-section, a Coulomb potential has an infinite range, right? And that's obvious because it's a long-range interaction. Any two electrons anywhere in space or any two Coulomb charged particles will interact, okay? So you have an infinitely strong scattering. And then what do you do in a solid? You essentially put together an infinite number of them. So you have an infinite number of infinitely strongly scattering objects. And that's going to be problematic. Of course, the chemists, one bit of this goes away because you can always truncate your system. You can have a small molecule or atom. You still have a big problem with the electrons, but at least it's truncatable in a way that isn't so obvious in the case of a solid. So the immediate reaction, surely, of everyone at the time is just, okay, let's see if we can do something useful with molecules because we might be able to make approximations, forget about solids. And a lot of what I say, actually, Volker Heine has written down in his sort of reminiscence of early days of electronic structure. And I have heard this story from other people as well. So there was this experimentalist who was in the Cavendish for one time. He went down to Bristol. This sort of moving between Bristol and Cambridge and Manchester was very, very common in all subjects. He was an experimentalist, and he measured the occupied bandwidths of lots of materials in the first row of the first two rows of the periodic table. And the interesting thing was that even if you take something like diamond, right, then the experiment showed that the occupied valence bandwidth was very close to what you would have calculated for a free electron system, a non-interacting electron system. Now, of course, it's nonsensical. Of course, the electrons interact. But what it meant was that early generation of theorists, you know, your Fermis, your Motts, started beginning to think, well, why is it that in certain circumstances, all of the complexity seems to disappear? And really, this is the story that I want to tell. Okay, so that's something that says, actually, it's as if, and not in all cases, obviously, but in lots of cases, it's as if the electrons aren't interacting with each other. So that gives us an enormous simplification. We can ignore electron-electron interactions. And of course, if you have a crystal, then you have translational symmetry, you have Bloch's theorem, and in fact, you only have to solve for a single unit cell. And you start moving towards the possibility, even for the days of big, powerful computers, of being able to look at band structures, electron dispersion curves. And there were two sort of, schools of approaching this. Conyers Herring was one. He was pushing the idea of orthogonalized plane waves. You have plane waves, but of course you have to have the orthogonality to core electron states. So you just basically orthogonalize your plane wave as it goes through the center of each atom. Now, I always find that when you're trying to sort of talk about what it was like a long time, and this is, I know I'm old, but I'm not even that old, okay? That everyone, of course, thinks about things from everything they know now, all right? And of course, now you're looking at that picture and you're saying, make me a pseudopotential, please make me a pseudopotential. I want to be a pseudopotential, I don't want to be an aunt. And it's kind of screaming out at you. Well, it was indeed this approach with a whole series of people. I think first of all was Jim Phillips and Kleiman. They were sort of the first people to start thinking about constructing pseudopotentials. But there is a flow that goes through to pseudopotential generation, which we're going to come back to in a bit. And then, of course, there was the other approach later, which is more sort of atom-based. And this was the augmented plane wave approach, where you solve within your atomic spheres and then connect these together. But of course, you could get rid of the connection and you could just increase your basis set. And then you've got all the sort of atom-based or bond-based techniques. And in some ways, you can see flowing from that. So now we get to good old Volker. I know a lot of you were able to say a quick hello to him last night. It was great that he turned up at the dinner. And so Volker arrived in Cambridge in the, well, it was 70 years ago. I think we sort of date the TCM group, Dirac and Lenz matter group, to his arrival, Mott's arrival in Cambridge, so the mid-50s. And I'm sure you've heard Volker, or those who've heard Volker talk at any sort of after dinner or informal occasion. He will always tell the story. If he arrived from New Zealand, he goes down because he wants to work with Neville Mott. So he goes to Neville Mott, the Cambridge professor, and says, what would you like me to work on? And Mott basically sends him away with the instruction, go and make yourself useful. Perhaps you could go and talk to the low temperature group. And that's what he did. And that philosophy of make yourself useful, I mean, that's not dissimilar to what Dirac was saying. Do something that is helpful. Yeah, I think it's a theme that I think TCM has managed to adhere to over many, many years. Okay, so it goes away. And there's the own OPW method, orthogonalized plane wave, and he uses it to calculate the band structure of aluminium. Actually, this is a diagram I hijacked from somewhere else, because when you look at his paper, it's just a series of energies at various points in the Breuer zone. So this diagram actually isn't from that paper. So why is this useful? Why is this relevant? Okay, well, it's useful and relevant because the 50s was when the Haas von Alpha measurements started getting to a very high quality. And one of the achievements of Brian Pippard, subsequently a Cambridge professor, was a measurement of the Fermi surface of copper through the Haas von Alpha measurements, which give you extremal areas of the Fermi surface. So you have to go around lots of orientations to put this back together. This thing underneath that representation of the Fermi surface, which you can see is very much like a free electron sphere, except with band structure effects. So it's now very familiar, but of course then was, far less known. That model used to be in the Cavendish laboratory in Cavendish 2, and I'm not sure if it's made it to the museum section here because there aren't so many things on display. But this is making yourself useful. Yes, you have this interaction between theory and experiment, with theory helping the experimentalists. Okay. Right, that's all well and good, but now, okay, and my talk is not sequential in time because it can't, because so many of these things were going on at the same time. Back to the electron-electron interaction. Okay, well, I mean, lots had been done with the electron-electron interaction. Anyone who's done a solid-state physics course will remember Thomas Fermi's screening model. So a density-based approach to deal with electron-electron screening. And then over the sort of 40s and 50s and 60s, you got a deeper appreciation of what was going on. Landau introducing the idea of quasar particles. As you switch on the interactions between the electrons, you start creating these quasar particles of electrons dressed by their screening exchange correlation holes. The rise of many body theory, and Hedin, I think, is widely acknowledged as being one of the people who brought those techniques most into solid state physics, best known for the GW approximation, which we've heard lots about today. And then at the bottom, actually I've cribbed this from Matthew Falk's lecture notes. Thank you very much, Matthew. And I presume this was done with the Casino code, probably with Richard. Yeah, from Quantum Monte Carlo, here is on your left, your exchange correlation hole at a particular point in the silicon crystal. And of course, at that point, you compare with the thing on the right, which is the local density approximation hole, exchange correlation hole. And of course, at that point in the material, they look identical, which shows that even something as crude as local density approximation at particular points is doing a very good job of describing the exchange correlation hole. Well, you don't need to move very far away from this point in silicon, and they will look completely different, which is why density functions, and particularly the LDA, are going to go wrong. Now, we have a meander. Because I think, at this time, you had the band structure approaches, you had other things which you're going to get to, and it was all about, okay, we've done the band structure, that's great. What are we going to do next? How are we going to help with the experimentalists? How are we going to actually move our fields forward? And it was not clear at the time. You had tight binding approaches. The chemists had their Huckelbeck, they're the same thing, yes? But something quite remarkable happened in Cambridge. So very much led by Roger Haydock, who's on the left, with Volker again, he's always going to figure, and Mike Kelly on the left. I couldn't find a picture of Dave Bullitt. He moved from TCM to Bath University. I couldn't find a picture of him. They developed with others in TCM, and I know some people here even sort of were working on the tail end of all this, a thing called the recursion method. And here we have, back in my days, there was a shelf full of these books called Solid State Physics. They were kind of like, the reviews of modern physics. If it was really important, you got into solid state physics, all right? And this volume, which was 58 solid state sciences, was entirely about the recursion method and applications. And given some of the talks this morning, the recursion method was basically a Lennard-Jones type method for diagonalization. It was linear scaling. You could apply it to any sort of short-ranged Hamiltonian, so your LCAOs or type binding or short-range phonons. And remember, we're going back to the 1970s, maybe, yeah, 1970s or so here. And look at this. 2,500 atoms. D-bands, yeah? Using that methodology. Oh, it's just remarkable, yeah? But of course, back then, say you took type binding, it was before we got to ab initio type binding, and so there was always the issue about the form of the type binding Hamiltonian. I remember endless discussions in the coffee era in TCM about the longer scale fall off of the type binding matrix element. So there's a degree of empiricism, yeah, which, you know, limited what you could do. But actually, if people had learnt from what was learnt here about how to structure clusters to try and get bulk properties, a hell of a lot of computer time would have been saved, but they didn't. Okay. Now, in a parallel strand, of course, mid-60s, we had Hermann-Cohn and then Cohn-Sham theory. And this was, was density functional theory. It was interesting when I said to Volker, when you had, density functional theory first came about, wasn't this really important? Because of course, in the solid state, people have been using the density as a way of trying to understand these complex systems with a sort of feeling that, okay, we don't have any choice. It's the only way we're going to do it. We're not going to be able to do wave functions. So I said to Volker, did this change it? Because suddenly you felt that everything could be done rigorously. And she was somewhat dismissive, saying, oh, we all knew you had to use density. Oh, whatever. Well, that's fine. But we had sort of foundation number one. I talked previously about, the pseudopotential came about by people thinking about what the orthogonalized plane wave method was doing and eventually developing a pseudopotential. So people who were influential here, obviously Volker, but it was Igor Abarenkov from Russia who came over and, talked with Volker about various ways of constructing pseudopotentials. In particular, the idea you just truncate the Coulomb potential at some point where it generates the right scattering. And Volker and Igor had endless arguments about this is completely unphysical, completely stupid, until Igor got the message across that the only thing that matters is the phase shift. And so it doesn't matter how you structure the pseudopotential, at least in terms of recreating the phase shift. And then the person at the bottom here is Alex Animalou, who constructed, again, this is remarkable, yeah? Constructed a database of 35 pseudopotentials for different elements. Okay, so we've got density functional theory, we've got pseudopotential, and of course, pseudopotential has lots of advantages. Lower energy scales, because it's smooth, you can use plane waves. And plane, we heard from Ali about, I've always said, point about chemistry and Gaussian orbitals is that, they're an absolutely appalling basis set, right? But of course, plane waves are an even worse basis set, right? And actually, I remember Richard saying this many years ago, whenever you had something happening in electronic structure, some development, some new idea, it was always the plane wave codes that implemented it first because it's so much easier to do in a plane wave basis, yeah? So it's a lousy basis, but it's so convenient, particularly with things that come later. Okay, and again, that's another solid state physics, Lennard tome dedicated to pseudopotentials. But of course, I couldn't resist. I went down to the library yesterday just to photo. Everyone remember this from Ashcroft and Mermin, 1976? If you can't read it. From such choices have risen a wealth of pseudopotential law whose usefulness for anything other than justifying a nearly free electron Fermi surface has yet to be convincingly established. 1976. Yep. The skeptics were always there. They're still there. And of course, I've talked about periodic cells. That doesn't just restrict you to crystals. We know how to embed a dimensional systems into large enough supercells and deal with long-range interactions. But you had a combination of elements that led to the plane wave total energy superpotential method. And to me, the beginnings of predictive calculations. You can probably argue, there are probably other papers out there. The 2-atom silicon, small unit cells showing that the diamond structure is the lowest energy, similarly for germanium, by Yin and Cohen back to 1982. And in some ways, you finally got there. As Dirac said, you got the atomic numbers. You've got a approximate method, quantum mechanical based, that you can solve, and then you can predict physical and chemical properties, which you did there, as long as it's for 2 atoms of silicon. And the chemists, of course, are making progress with full CI. And I think at about the same time, and of course it does coincide with the arrival of big computers, then quantum chemistry, or in Cambridge, theoretical chemistry, I remember being corrected on that point by David Buckingham. You had these 2 different camps, and as Ali said, we didn't necessarily communicate very well. It was like a battle. All right, there was a decade, it was great. Every time you went and presented a density functional theory calculation, the chemist said, well, it's not an issue, doesn't work. All right, and then we just said, yeah, but you can't converge the basis. Yeah, pathetic, really, but never mind. It was quite fun. But there was this pressing need to be able to make predictive, definitive statements to help the experimentalists. The 80s were the rise of heterostructure engineering, gallium arsenide, aluminium gallium arsenide structures. And you would go to conferences and everyone would argue about the band alignments of the 2, which is absolutely critical to the devices and the states. And you basically did whatever number you would like, and everyone argued about it till someone did. And it was in the very early days of superpotential calculations, actually in other methods as well, because I think Richard Martin did it with full potential. You could actually predict the band offset. And actually one of the most remarkable things is once there was a theoretical prediction, suddenly every experimentalist agreed it was right. That is worrying in itself. And I just showed another picture. This is a potential energy surface for a surface chemical reaction. Well, we've heard all about that from Jens. Yes, we've made some contributions, but it's very much an ongoing question. But these things need some insight where the answer you get out is reasonably reliable to the point of being useful to experiments. So how did Cambridge get into this game? Well, Volcker, of course, immediately saw that this was important. And he sent Richard Needs off to work with Richard Martin, who was then at Dirac's Palo Alto Research Center. Richard was there for 2 years and then came back to Cambridge and started doing these big calculations here, okay? And just, Richard did lots and lots of things in this area before he then moved on to quantum Monte Carlo. But this is an absolute tour de force, right? This is, late 1980s, right? This is the change of the band gap of silicon due to the self-energy due to interaction with phonons as a function of temperature, so you get the different occupancy of the phonon modes. It was the calculations done by Dominic King-Smith. So that's the self-energy of the HOMO and LUMO in your chemistry language, the 2 states either side of the band gap. Dotted lines on the left are experiments. Subsequent experiments did bring them closer to these calculations, but an absolute tour de force, yes? So, something else was happening, though, in 1985. There was, these 2 people called Roberto Carr and Michele Parinello came up with a different way of doing the same type of plane wave superpotential calculations. They say this will allow us to do big systems. Actually, the original paper was just on 8 atoms of silicon, which everyone was doing, but it was clearly, well, for some people, it was clearly the way of the future. And this is where John Giannopoulos comes in. He and Roberto, is it right? You were both at IBM consulting, because that's what American professors do. So the moment that John, who already was doing total energy superpotential calculations, immediately he saw that this was the way of the future. So like all American professors, what does he do? He flies back to Boston and then flies up to Corning for another day's consultancy with Corning Glass, talking to Mike Teeter and Doug Allen, which produced the plane wave code that Biosim sold for a time, and that then became the Abinit code. So why is it density functional theory comes to Cambridge **2? Because John did finally come back to Cambridge, USA, MIT, called a group meeting and told me I was going to write the code, which was a bit of a shock to the system, who's someone who doesn't like computers, and then squared because then I came back to Cambridge. All right, and so we're in a rare condition where we actually had 3 people in TCM doing electronic structure. At the time, my view, and the view pretty well globally, is that any physics department can at most tolerate 1 electronic structure theorist. So it was unusual. All right, Berkeley was an exception. All right, but that rule was universal apart from Cambridge. All right. But the battles didn't end. So Roberto, John traveled a lot. Lots of groups in the States tried the car parallel method, and he was told by all of them it didn't work. Did you have the same experience?
Well, I remember that it was the summer of 85, I think, or 85, yes. And Michele and I were spending a few months at IBM in Northtown Heights. And John came visiting IBM, and I had a discussion with John where I explained to him what we were doing, and he was immediately impressed. And
yeah, well, he traveled the States a lot, and other groups had tried to make it work, and they all claimed it didn't work. So they didn't believe. We still had the chemists saying that density functional doesn't work, so that's just taken as granted. Okay, let me tell you some of the things I heard when I came back, Cambridge, and sort of, started developing what eventually became CASTEP. So really supportive statement number 1 from the electronic structure community and the physics community in the UK is, why would anyone want to do a quantum mechanical calculation on a system consisting of more than 10 atoms? Okay. And then when we kind of got to a global leadership position, but didn't you know it's not the role of the UK to be world leading in science? All right, it's just unbelievable. Anyway, it took a long time, number of developments. Within 5-6 years, we created what was called the CASTEP code. And this was always a selling point. We moved away from this, you can do whatever you like as long as it's 2 atoms silicon, to you really can do most of the periodic table. Lots of it won't work because it's DFT, but never mind, hundreds of atoms. You can do structural optimization because the forces come really cheap. Dynamics, so sampling of phase space, so that's what Roberto and Michele did for us. And wide range of scientific questions were addressable. And I guess, for us, one of the things that was important was for the time to make the technology as easily accessible. It's nothing like as good as now, but accessible. We would, give the code to people in sort of, geological sciences, and they'd do minerals. We'd give the code to people who did, X, Y, Z, because the complexity had been abstracted out when you had a guaranteed convergence. But still, the chemists didn't believe us, right? So you think, how do you convince the chemists, right? Well, of course, chemistry is just chemical reactions. So we did a chemical reaction. I can't show very much of it. I will just show the beginning of this because it gives the acknowledgements of the people who contributed, one being Sandro De Vita, who was mentioned yesterday by Nicola. He was one of the people involved in this. You look at the video quality, it's really lousy quality video. No, this was done with pre-production software because the software for visualizing atoms and reactions and things like that, things we take for granted now, didn't exist. It really was a different world. Okay, so obviously we did things that everyone does. Oh, why is it humming? Right, let me take you there. And of course, what do we get out of all this? We get charge densities, atomic positions. This is the final. So electrical chlorine molecule comes down onto a surface. Yes, the surface moves. Gosh, the surface moves. And you think, oh, the chlorine on the left is getting away, but look at that, the silicon goes chasing after it. It's a bit stupid, all right? If the energy changes with position, which obviously it does to get a chemical reaction, then that means there are forces. But, actually that was a bit of a shock to quite a lot of people. And Nick Handy was mentioned briefly in Ali's talk. This pretty well brings me to the end. We had this video back in whatever it was, 1991, 92. Dave King was professor of surface science in the chemistry laboratories in Cambridge. He heard about it, so I went down and showed the video. Nick Handy wasn't there, but he clearly heard about it the following day. And I have two independent, so two, not just one, two independent witnesses, right? Who basically said Nick Handy was seen wandering around the chemistry laboratory the following day, muttering, quantum chemistry is dead, quantum chemistry is dead. And within 6 months, he had produced his 78 parameter density functional. And within 18 months, pretty well every theoretical stroke quantum chemistry group in the world had added density functional theory to what they were doing. Which, okay, and then of course, yeah, like the rest is history. Of course, everyone would like to pretend, oh, it was entirely due to me. It wasn't, okay? You know, here are your citations. I mean, sorry, Roberto, but it did take a long time for what you did to have real impact and take off, yes? There's the chemists pretending they invented density functional theory. I was there, they didn't, they've never apologized, okay? But yeah, there were all the other things that were important, all right? It's very simple why the physicists loved it, the chemists didn't believe it worked, okay? We can talk about that afterwards, I don't want to talk about it now. One of the most important things being that the extensions of density functional theory that actually kept the sum rule on the exchange correlation hole. So the first proper GGAs, rather than the rubbish GGAs, were coming in, and everything conspired together. And of course, the rest is history. And that's the end of what I want to say. Thank you.